So today we are going to start our series of lectures on the frequency response of linear systems. So before we dive into this topic, I want to give you guys a little bit of context here. So we are going to be still continuing to do circuit analysis in the S domain here. But we are kind of shifting gears a little bit in as much as we're not particularly going to be interested in how things are behaving in the time domain anymore. We're going to be looking at how they behave in the frequency domain, which we are all arguably familiar with. Some of the methods and techniques that I'm going to introduce today and over the next several days are going to get reused in many of your upper level classes. So this frequency response of linear system stuff that I'm going to be teaching you guys today, we're going to revisit this in your electronics classes when we talk about the frequency response of the various types of amplifiers that we're going to learn how to construct. It's also a fundamental building block of what you're going to be doing next quarter in your electrical engineering 321 class. And then for those of you that go into controls, it'll show up again there. For those of you that go into communication systems, it'll also show up again in there. For those of you that go into integrated circuits, it'll show up there. I don't know whether or not it shows up in power systems or not, because it's been a very long time since I took that class. I don't particularly remember it. That being said, I'd be willing to bet you could find a way to force it to fit into there as well. Okay, so this is like fundamental type stuff. Okay. So the first thing that we're going to talk about today are transfer functions, poles, and zeros. We have briefly touched on transfer functions in this class, as well as in circuits 3 for circuits 2 for those of you who took me and when we talked about filters and all that kind of stuff, we dealt with frequency response. So we'll more formally do things here. Okay. So frequency response of a networker system is best described by looking at its transfer function, where a transfer function h of s can mean a couple of different things, right? So our transfer function h of s could be the output voltage in the S domain divided by the input voltage in the S domain. So in this sense, our transfer function describes the frequency dependency of the voltage gain of our system. When we looked at our simple first and second order filters in circuits 2, this is exactly the representation of the transfer function we were looking at, except that we were looking at it as h is a function of omega because our output and input voltages were functions of omega. Now we're simply including the fact that maybe omega also has some real part to signal, right? If instead our transfer function were defined to be the output current divided by the input current, then our transfer function would be the frequency dependence of our current gain. We could also define h of s to be output voltage divided by input current, in which case this would look like a transfer impedance. And finally, we could define h of s as I out over, Vn, and this would be some measure of the transfer admittance of our system. when we're looking at transistor amplifiers, we kind of get to choose our own adventure as to whether or not we want to look at things in terms of voltage gain or in terms of transfer admittance, just because of the way that transistors work. So, for example, in a transistor amplifier, the core functionality is the ability of well, actually, I guess it would be a transfer impedance. The core functionality of a transistor amplifier is its ability to convert some input current into some output voltage, but that input current is also dependent on some input voltage. So we could look at it as a ratio of the voltage gains or as transfer impedance multiplied by something else. And that'll make a lot more sense once we start talking about transistor amplifiers in later classes. Okay. So what I want us to do here is I want us to look at an example and simply determine what the transfer function of this particular circuit is. Okay. So our circuit of interest is this guy right here. We have some time domain input voltage Vn of t, some resistance R1, some inductance L, some capacitance C, some resistance R2, and then we are going to define our output voltage in this case to be the voltage drop across our resistor R2, right? So this is what our circuit looks like in the time domain. We want to look at the frequency dependence of our transfer function, which means we need to convert this into the S domain, right? So in the S domain, we would have Vn of S, our resistance R1, our inductance will have an impedance of SL, our capacitance will have an impedance of 1 over SC. Here is our resistance R2. Here is our output voltage, V out of S. So I have a specific way that I've worked this out, but before we probably wind up doing it my way, does anybody have any thoughts on how we might analyze the circuit in order to figure out the relationship between V out and V in? So I think I heard something about there being 2 nodes. That's definitely one way that we could do it, and it's not the way that I'm going to do it. So a source transformation is another way that we could do it, also not the way that I would do it. The reason why I wouldn't do a source transformation here in particular is because this isn't really a great reason, but I'm going to lose V in when I transform things. It's going to get carried through, but algebraically it's going to be a little bit messier than the way that I wanted to do it. So let me tell you guys how I'm going to do it, or at least how I did it. Take it for what it's worth. I'm going to define the voltage drop across my inductor to be V1 of S. And I'm going to define my transfer function. H of S is V out over V in. I'm effectively going to break this into stages. So I'm going to say that H of S is equal to V out over V in could be thought of as V out divided by V1 multiplied by V1 divided by V in. So I've broken this down into two separate stages that I can figure out my transfer functions literally just using voltage division rules. Just as a heads up, this is widely used, once again, in transistor amplifier circuits where we want to break things down into bite-sized pieces that we can easily recognize and then chain everything together. So let's start by figuring out what V1 is. So using voltage division, I'm going to say that V1 is Vn multiplied by, so now I want the impedance that I'm trying to find the voltage drop over, which to me is this impedance SL in parallel with the series combination of R2 and 1 over SC. So that's going to look like SL times R2 plus 1 over SC divided by R2 plus SL plus 1 over SC. All of this, I need my bracket to be larger apparently. It's going to be divided by R1 plus that exact same expression in the numerator. All right, so now I need to make this look less horrifying because in its current form, it's pretty gross, right? So what could I do to fix some things here? Well, I would argue that if I multiply by the numerator by SC over SC and the denominator by SC over SC, I can make this look slightly less awful, right? So that would be Vn of S multiplied by, so multiplying the numerator of my numerator by a factor of SC is going to give me SL times SR2C plus 1 divided by S squared LC plus SR2C plus 1. Are we okay with that? My denominator is just going to look like R1 plus that same thing. I hear whispering. What's the question about? Yes. I am not, because I am multiplying by SC over SC in both the numerator and the denominator. So I'm multiplying by 1. So it'll cancel itself out there. Was that what the whispering was about? Okay, so just to be clear, I'm multiplying by SC over SC and then SC over SC so that I should not have anything fancy here. Now, what I'm going to do is I'm going to multiply R1 by the denominator of my denominator. over that same thing so that I have a common denominator here so that I can get rid of things. Right? So this would be Vn of S is equal to, my numerator is going to stay exactly the same, SL times SR2C plus 1 divided by S squared LC plus SR2C plus 1. Then I'm going to have S squared times R1 LC plus S times R1 R2C plus R1 all divided by, oh, sorry, I need to keep this going, plus SL times SR2C plus 1. That whole thing divided by S squared LC plus SR2C plus 1. So just to be clear here, this whole first term, let me put parentheses around it, should literally just be this R1 multiplied by this denominator. So I had S squared LC, now I have S squared R1 LC. I had SR2 times C, now I have SR1 R2 times C. I had 1, now I have R1. So that's just this denominator multiplied by R1 so that I get a common denominator. Since the denominator of my numerator and the denominator of my denominator are the same thing, they cancel each other out. And that, in turn, leaves me with the relationship Vn of S, sorry, that shouldn't be equal, that should be multiplied, times SL times SR2C plus 1 divided by S squared multiplied by R1 LC plus R2 LC plus S times R1 R2 C plus L plus R1. Where I'm simply lumping together my S squared terms, my S terms, and my constant. Algebra checkout, Brody. From here, my first stage transfer function, sorry, V1 of S divided by Vn of S is just that exact same thing except without the V1 out front. So SL SR2C plus 1 divided by S squared R1. Let's lump these together. LC times R1 plus R2 plus S R1 R2 C plus L plus R1. Now I need to figure out what the relationship is between V out and V1. scroll up here. And I'm going to do that literally just by doing voltage, right? So it should look like R2 over R2 plus 1 over SC. Multiplying by SC over SC gives me V1 times SR2C over SR2C plus 1. And so my transfer function for this stage is just SR2C over SR2C plus 1. And from this, my overall transfer function, H of S, is just these two transfer functions multiplied by each other, right? So SL times SR2C plus 1 divided by S squared LC R1 plus R2 plus S R1 R2 C plus L plus R1 multiplied by SR2C over SR2C plus 1. We can see then that these guys cancel each other out. And we are left with SL times SR2C divided by S squared LC R1 plus R2 plus S R1 R2C plus L plus R1. So this is our transfer function. We could, if we were so inclined, yes. Yes. So if we were trying to take the inverse Laplace transform of this thing, this isn't really the form that we would want it to be, right? So we can make a couple of quick fixes here just to pretty this thing up to some extent. Okay. So for instance, I could factor out a term that would look like R2 times L times C divided by 1 over LC times R1 plus R2. And then I would just have S squared in the denominator, and then S squared plus R1, R2, C plus L divided by LC R1 plus R2, this whole thing multiplied by S plus R1 over LC times R1 plus R2. And that's more of the form that we are used to, where we have effectively some constant value C multiplied by a numerator as a function of S and a denominator as a function of S. So this is what my quote unquote final form of this transfer function would be. Realistically, since I have R2 times L times C divided by this reciprocal, I would just multiply this R2LC by this thing right here and pretty that up again, but I'm bored, so I don't want to do it. All right, so we have our transfer function in a nice, neat form where we have some constant multiplied by a numerator as a function of S and a denominator as a function of S. Okay. So now that we've covered a transfer function, let's talk about zeros and poles. Anybody have any idea what zeros mean? So the zeros are the roots of the numerator and the poles are the roots of the denominator, right? So this system, we should expect to have two zeros because we have a second order polynomial in the numerator, and we should also expect to have two poles because we have a second order polynomial in the denominator. Yes, Siobhan. You're saying this bit right here should be in the numerator? I disagree. I am multiplying this whole thing right here through by a factor of when I take it out from here, dividing. So either both of them should be in the numerator or neither of them should be in the numerator. This is algebra stuff that I should probably be better at. Let me. Yeah, so I should be multiplying through by this thing here and here, not dividing through. It's so what perturbs me about this, I'm perfectly acceptable or perfectly fine with being wrong. You guys know it happens rather often. That being said, when I put this into my math cat sheet, I did get literally the same poles and zeros as the unsolved thing here. Oh. So I'm getting rid of this factor here. I should be dividing it here and here. So out front, I should multiply instead of divide. Okay. That's easy enough. Done. All right. Okay. So, okay. So regardless of my algebraic mistake here, we have a second order polynomial in S in the numerator, so we're going to have two zeros. Second order polynomial in S, we're going to have two poles. So for our zeros, just to be clear here, we've already said it. We want n of S to be equal to 0, which means we want S squared to be equal to 0, which in turn gives us the following zeros. So omega z1 will be equal to omega z2 will be equal to 0 radians per second. So we have two repeated zeros at 0. For our poles, we want our denominator as a function of s to be 0. So that means we want s squared plus this big ugly thing, r1 times r2 c plus L divided by LC R1 plus R2 times S plus R1 divided by LC times R1 plus R2 to be equal to 0. And we can use the good old quadratic formula to figure out what the value of those poles will be. So that's going to look like negative R1, R2, C plus L divided by LC times R1 plus R2 plus the square root of that thing, R1, R2, C plus L divided by LC R1 plus R2 quantity squared minus 4 R1 over LC R1 plus R2 divided by 2. And then our pole omega P2 is going to be literally the exact same thing, but we flip it to a positive sign, or excuse me, a negative sign there. So I'm just going to put dots here minus the square root of this whole thing over 2, where it's literally the exact repeated thing, and I'm just running out. So let me put this here. So let's say that we had R1 was equal to 200 ohms, R2 was equal to 100 ohms, L was equal to 10 millihenries, and C was equal to half of a millifarad. We would obviously still have omega Z1 is equal to omega Z2 is equal to 0. We would also wind up getting a pole at negative 20.040 radians per second, and a second pole at negative 6.653 times 10 to the 3 radians per second. So I'm about to draw what's called a pole zero constellation for this system. Okay. And so on a pole zero constellation, our vertical axis is corresponding to omega, so that's the imaginary part. Our horizontal axis is corresponding to sigma, the real part. And so this is just a plot of the S plane, right? So in this particular case, we would have 2 zeros at our origin. I identify a 0 by putting a circle there. And then I'm going to have a pole, which we indicate with an X at negative 20.04. And then another pole way out here at negative 6.653 times 10 to the 3. So we can see that both of our poles are on what we call the left-hand plane. We don't have anything going on our vertical axis, and we have nothing going on in our right-hand plane whatsoever. So this particular type of system would be called a stable system. Okay? So when we have a pole zero constellation, if all of our poles are in the left-hand plane, doesn't matter if they are distinct real poles or repeated poles or anything like that, we have a stable system. So if everything is to the left of here, our system is stable 100% of the time. Our inverse Laplace transform is effectively going to yield exponentially decaying signals, right? If instead we had poles on the right-hand plane, we would have exponentially increasing signals, which would mean, or which would, indicate instability, right? Because for a very small input signal, over time, our output would approach infinity. So we have an unstable system if our poles are over here on the right hand. What happens if we have poles on the axis? So let's say that we had, let me do this in a different color. So we have a pole here. Let's just call this at 0 plus J10, and down here at 0 minus J10, because we know these should come in complex conjugate pairs. What would this indicate? A sinusoidal signal, right? So we would consider this to be marginally stable because we have built an oscillator. If our transfer function results in poles that are on our vertical axis, we have an oscillator. If they are repeated poles, we have an unstable system. Okay. So just to recap things, and let me write this down. If all poles are on the left-hand plane, we have a stable system. If any poles are on the right-hand plane, we have an unstable system. If poles are on the vertical axis, we have discrete poles. That indicates stable. Excuse me, this should be repeated poles. Actually, let me put this, instead of stable, marginally stable. What we mean by marginally stable is that a small perturbation can push it towards stability or instability. So these are what our pole zero constellations will look like. So at present, we have a transfer function that is of the form k times, in this case, it's going to be s squared over s plus 20.04 times s plus 6.53 times 10 to the 3. Now, how do we turn this representation of our transfer function into something that we can build what's called a Bode plot out of, where a Bode plot is a graph of our frequency response under special conditions. And that special condition is the vertical axis is a log scale plot of our ratio. So we want to transform this thing into the following form. Actually, sorry, this should be C here because that's what I was using earlier. We want it to be of the form K times S squared over 1 plus S over omega Z1 times 1 plus S over omega Z2. This form is what's called our standard form. And our standard form is what's used to construct Bode plots. So anybody have any ideas how we're going to get from this representation, which we currently have, to this representation? Divide by the Hall frequencies. That's literally it. So this K is literally just C divided by omega P1 times omega P2. If we had, so just to be clear here, let me do this in this blue form. So because our poles are, excuse me, because our zeros are at 0, this makes this a little bit awkward. But generally speaking, we would have S plus, excuse me, yeah, no, that was right. S plus omega Z1 times S plus omega Z2, etc., divided by S plus omega P1 times S plus omega P2, etc. And the form that we would be looking for would be 1 plus S over omega Z1 times 1 plus S over omega Z2, all divided by 1 plus S over omega P1, 1 plus S over omega P2. That's the true standard form, but because we have S, because we have zeros at 0, that's what it's looking like. Yes. You're absolutely correct. Thank you for that. So these shouldn't be Z's in the denominator, they should be P's. Thank you. What happens when I spend all weekend making out a circuit one test and trying to remember how to do this from scratch. All right. So in this case over here, our C would just be multiplied by a factor of omega Z1, omega Z2. That's just trying to illustrate what's going on there. Okay, so what should K be for this thing? Since I made a mistake in my notes, I need to go to my calculator really quick. Scroll up here so I can see it. So R2, 100 times 10 times 10 to the minus 3, 0.5 times 10 to the minus, oh, well, those LCs just cancel each other out, so that's way easier actually. So 200 over 300, that's easy enough, 2/3. I'll be damned. negative 20.04 and change, negative 6.653 times 10 to the third and change. Four, five, six. Answer divided by 10 to the minus 6. $5.00027 and some change times 10 to the minus 6. Right? So, yes. Did I screw up now, Brody? Plus, plus. Answer's the same. All right. So we have this number right here. This is our constant value K. What we're going to do now is we're going to put K in our decibel scale. Okay. So I need 20 log of K will be equal to some number in decibels. And because that number is significantly less than 1, I'm expecting a negative number, right? So 20 times the log. That's the wrong button. 5.00027055 times 10 to the minus 6 is negative 106.020 decibels. It's actually larger than I thought it would be. I thought it would be smaller than that, but that's okay. All right. So now, what's up? Sure, absolutely, because I feel like I'm butchering this too. All right, let's scroll up here. R2, actually, it might be supposed to be 1/3. Is R2 100? Yeah. Okay, it could be 1/3. My bad. Yeah. All right, try this again. 1/3 divided by positive, Rody, 20.04, 6.653. No, I genuinely, if you guys catch me making a mistake, please tell me. 2.5 shouldn't have been that hard to figure out. Times 10 to the minus 6. The 20 times the log of 2.5 times 10 to the minus 6. Negative 112.041 decibels. Yes. This 20 right here. Okay. So in decibel scale, decibel is usually a ratio of powers. Okay. So if we want to find the power in decibels, this is an aside here. We would have 10 log of, let's call it the output power divided by the input power. That is what the decibel scale is literally based on. So whatever this gives us will be measured in decibels, okay? Now, what? Just the constant out front of our form. Okay, let's some constant number. Yep.
I was thinking it was the past.
Nope. Okay, so that's, I can see why that would be confusing. I'm using the same symbol for two different things. No. So I want this of a form to where I have some constant number multiplied by a polynomial in S in the numerator divided by a polynomial in S in the denominator. Okay. Nope, good questions. Looking like more and more of a jackass every moment I'm up here. It's okay. All right, so the output power is going to be proportional to the output voltage, right? So this would be 10 log V out squared divided by Vn squared, which is the same thing as 20 log V out over Vn. So when we're dealing with a ratio of voltages, to get our answer in decibels, we use a factor of 20 out front. When we're dealing with powers, we use a factor of 10 out front. Because power is proportional to voltage squared. You look incredulous, but that's literally how it works. I don't fault you for your incredulousness, given how today has gone thus far. All right. So we have this number, negative 112.041 decibels. And then we have two zeros at omega is equal to 0. We have a pole at omega is equal to 20.04. We have a pole at 6.653 times 10 to the positive 3 radians per second. So we're going to take all of this together and construct a Bode plot. So I'm going to open up another sheet of paper here, and I'm going to provide you guys with this sheet of paper as well. Let me find it. Dropbox. Semi-log paper for Bode plots. I named it something obvious. Yes. Bode, B-O-D-E. And then plot is the word plot. Named for a dude with the last name of Bode, if I am not mistaken. Might have been a lady, but I think it was probably a dude. All right, so I'm going to just call this, for the sake of argument, negative 120, negative 100, negative 80, negative 60, negative 40, negative 20, 0, positive 20, positive 40, etc. And then we can never get to 0 here. So let's just do 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and so forth. All right. So I'm going to come in at somewhere around negative 112 decibels. And because I have two zeros at S is equal to 0, what I should see, all right, so I guess I should talk about these rules here really quickly. So zeros mean increase at a rate of plus 20 decibels per decade. Poles mean that we decrease at a rate of negative 20 decibels per decade. All right. So again, I'm saying that because we found that our constant term should be somewhere in the ballpark of negative 112 decibels, which would be right around here. So this is our constant term K. We should start this thing by increasing at a rate of positive 40 decibels per decade because we have repeated poles at 0, right? So if we started at negative 112, we should be about here. That's 20 decibels. Actually, no, that would be 40 dB, right? So in 1 decade, we have increased by 40 decibels. So that is the rate at which things should be going. Connecting dots here. At 20, we had a pole. So we should be decreasing at a rate of negative 20 decibels per decade. Oh, actually, my bad. Because that's starting at 10, we want it at 20. And then also at 6,000 and some change. Yes. You're right. Damn it. 20 would be 2 times 10 to the 1. Thank you, North. Something like that. And then over here at 6,000, so let's see. So 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. Something like that. Maybe I should have started this thing at 10 to the 0, but it'll be okay. So when we're trying to put all this stuff together, we should effectively see that up until we hit this point roughly, we're increasing at a rate of 40 decibels per decade. Now we're about to shave 20 decibels per decade off because we hit our first pole. So let's see here. Oops, I overshot it. We're going to continue at this rate until we hit, imagine I could draw a straight line on this thing, until we hit about 6,000, at which point it would wind up flattening out, right? So this is a very shittily drawn Bodie plot. Yes, ma'am. How am I doing what? So I'm starting at as close to 0 as I can get, increasing at a rate of 40 decibels per decade because by 2 zeros at by 2 zeros at S is equal to 0. At this point where I hit 20 is where I hit my first pole. So that means my rate of increase has dropped from 40 decibels per decade to 20 decibels per decade. I continue increasing at a rate of 20 decibels per decade until I hit omega is equal to 6 times 10 to the 3, at which point my rate should decrease to 0 decibels per decade or a flat line because my 2 poles have canceled out the rise of my 2 zeros. So for every zero we have, we increase at a rate of 20 decibels per decade. There were 2 zeros at 0, which is why we're starting off with this 40 decibel per decade increase, right? So we have repeated zeros. So we have a 40 decibel per decade increase. At this point right here, I have hit my first pole. So I should see that my rate decreases by 20 decibels per decade. So 40 minus 20 is positive 20 decibels per decade. So now I am increasing by positive 20 decibels per decade until I hit my second pole. My second pole occurs at 6 point something times 10 to the 3. Now my rate of 20 decibels per decade gets 20 decibels per decade subtracted from it because I hit my second pole and we're effectively flat. So at very, very high frequencies, we should see that the output of this thing is effectively constant.
So the rates only depend on how
many poles or zeros?
So the locations of them depend on what values we have for omega P1 and P2.
Correct. Yes. Yes. So if we go back to the other thing here, typically speaking, you get to use a ruler to do this as well. Our poles are at 20 radians per second and 6,600 radians per second. So if we go to this thing, this is 10 to the 1. So this is 10. One thing over is 10 to the 2, which is 20. So that's why I chose there for my first pole. Way over here, I have 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. So this is ballpark to where this one should be. Yes, Daniel. The frequency response of our system, right? So this is looking like a high pass filter, right? So as we increase in frequency, our output signal gets larger and larger and larger. If we had, let me do another paper here, right? So let's see, edit, remove annotations. So let's say that we had a signal or whatever, or a transfer function h of s that looked like (20 decibels times (1 plus s over 10 to the 2, 1 plus s over 10 to the 3. Down here we had (1 plus s over 10 to the minus 1, 1 plus s over 10 to the 0. So this is as easy as I can make it, where all of our poles and zeros are at 10 to the something so that I can draw this without looking like a complete utter jackass. All right. Just for the sake of argument, let's call this 0 decibels, this 20 decibels, -20, -40, -60, -80, -100, -120, and so forth, right? So our baseline is at 20 decibels. I think I did that one in red. So let's just fill this thing out in red. So it's right on the axis. Everything is easy peasy. All right, we have a pole at, oh, I need to define my time axis down here. So let's make this 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2. And I'm running out of space, so 10 to the 3. Yeah, that'll be okay. So at 10 to the positive 2 and 10 to the positive 3, we would have a line that looks like that, and then we would also have another one over here, but we kind of ran out of space on our frequency graph. We have a pole at 10 to the minus 1. That's going to keep on keeping on. We also have a pole at 10 to the 0, if I'm not mistaken. So putting all of this together, we would be at 20 decibels until we hit our first pole. Then we would decrease at a rate of 20 decibels per decade. Then we're going to start decreasing at a rate of 40 decibels per decade because of our second pole, right? Forty decibels, there's one decade. When we get to 10 to the 2, shit, I didn't mean to erase that. We hit 10 to the 2, we get another, or we hit our first 0. So now we're going to decrease at a rate of 10 decibels per decade. And then from here on out, we would be decreasing at a rate of 0. Yes. So okay, so let's talk about that a little bit because this has always been something a little bit confusing as well. Okay. What does a negative frequency mean? Right? So all of our S values and all that kind of stuff that we've been dealing with, if we have a stable system, we're expecting our S value to be a negative quantity. What does a negative frequency mean? The exact same thing as a positive frequency does. So our signs here really don't make any difference whatsoever. The signs are only going to affect our system's stability or instability. But from a perspective of a Bode plot, it doesn't matter in the least. And if we have time, we probably actually won't have time in circuits 3, but definitely later on we'll talk about interesting things like phase margin and gain margin and all that kind of stuff so that you can use concepts like feedback in order to fix your system's instability and make it stable over frequency ranges of interest and all of that kind of jazz by bootstrapping things. Yes.
If it were an unstable system, I mean, it would flatline at 0 at the end.
Yeah, so effectively, if it were unstable, it would continue to increase positively forever. So if it flatlines, we're good. If it continues decreasing forever, we're also good. Because realistically, we should always have an infinite number of necessary zeros or poles at infinity to make it flatline effectively at omega is equal to infinity. All right, we are out of time. We will revisit this concept a bit more on Wednesday.